Okay, welcome everybody. Today we have a very interesting talk by Steve Boudreault. I think that probably most of you know him. He has been doing a postdoc in the ISC during the last 1 year and a half or 1 year. Yeah, well, he made his PhD in Germany in the mass plants at Heidelberg. And then he was doing a postdoc in England and came here to the ISC. I think I had not mentioned, but today is his last day working here. So, well, only say thank you for being here, and well, let's see. We will see today a very interesting results in the Praesepe cluster, the discovery of and the confirmation of the first L dwarf. So, thank you very much, Steve.
Thank you for the introduction. So, as Victor mentioned, I will present the result of actually the first spectroscopic confirmation of an L dwarf in Praesepe using observation with the OSIRIS spectrograph at the GTC. This is a work I done with my PI, Nicolas Laudieu. So, a brief summary of my talk. I will present you the motivation, the survey in open cluster, and why spectroscopic follow-up of low mass object. I will give you more detail on the survey of Praesepe, done with photometry and astrometry using UKITS data. Then I will talk more about our L dwarf candidate, presenting spectral type, effective temperature, mass, and discuss about the membership. And then I will give a few words about future work. Okay, so briefly, why care about mass function in open cluster in the low mass regime? Well, of course, it's for different reasons. Of course, you can use mass function to study the age, the metallicity. There is still the issue if the IMF is universal. These are two review papers in the topic from Nate Bastian and Demarchi that you can look for reference. In this case, they were looking for variation as a function of H. Sorry. You can also use the mass function to study the distribution of object in cluster without having to look at the special distribution. For instance, in the upper left, I present mass function on the star formation region EC348, in which they were comparing the core, the halo of the cluster as a function of mass. Also, I did this for EC239 in my thesis, and we also did this for Praesepe in our work that I will present, comparing the inside of the core compared to the outer region. Okay, but now word contamination. Of course, if you only do a photometric survey, you may have more contamination than if you combine this with astrometry. This is a very good example. The mass function we had in Praesepe was different than previous determination. As you can see, previous determination were showing a rise, while we had a decrease between 0.6 and 0.01 solar mass. And this was because previous survey were added contaminated. This is an example of a color magnitude diagram in Z versus Z minus J, in which you can see a lot of object from the field, and you barely can see the sequence. Now, if we are performing a 3 sigma astrometric selection, this is what you have, or the same color magnitude diagram, and then you can clearly see the sequence, including the sequence of the binaries. And then you may ask, okay, well, if astrometry is very good in removing contaminant, is a spectroscopic follow-up really needed? The answer is yes. An example is for, on the right, you have a radial plot of Praesepe cluster, and this is from another work with alpha pair. You can see that even with photometric selection in several bands and astrometric selection, you may end up of having a contamination rate of up to 25%. And in alpha pair, in the subsolar regime, it was up as 50%. So it's very important to clear a sample while doing spectroscopic follow-up. And then you may ask, why do we would care about brown dwarfs and L dwarf? Well, the problem is that there is a lot of L dwarf knowns in the field and also in very young populations. So you have a big gap between 10 million years and 1 gig a year where you don't have too many confirmation by spectroscopy of L dwarfs. You have, for instance, cluster in the Pleiades where you have L dwarf that were observed spectroscopically by Gabriel behind. And you also have, for instance, L dwarf candidate in the Ides, but no spectroscopic follow-up very much in this age range. So why Praesepe? Well, Praesepe is indeed having an age that is in that gap. It is relatively close compared to other clusters, for instance, NGC 2516 and the Orion Nebula cluster, which are more at 400 parsec. The astrometric position of the Praesepe is relatively high, so you can perform good astrometric selection, like I've shown you previously. And also the reddening towards the cluster is relatively very low. So our survey was using UKIT's data, the Galactic Cluster Survey, the data release 9. The total coverage was 36 square degree, and we were going down to 19.3 magnitude. In solar mass, that's roughly around 0.06 solar mass. We did an astrometric selection, as I've mentioned previously, of 3 sigma around the location of the cluster. And we also performed a photometric selection in 4 different color magnitude diagram, in which we were taking everything that was 3 sigma bluer than the sequence and everything redder. So all these results are present. From this, we had 1,000 candidates, and this was presented in a publication last year. Now, about our L dwarf candidate, we got the spectra with a spectroscopic campaign that was with OSIRIS at the GTC, where we were observing candidates with masses lower than 0.1 solar mass in Alpha Pair, Pleiades, and Praesepe. I also gave you the setup we had for the observation, very low resolution, but this was needed to observe our very faint target. The color of the L dwarf candidate in Praesepe had this color. If we compare with previous object known, the open circles are some M dwarf, stars are L dwarfs, and the triangles are T dwarfs. This is taken from this work. The black dot were basically L dwarf candidates we had for another project. Basically, our object in Praesepe is related, this position of the L dwarf candidate is here, very close to the other L dwarfs. The observation, in total, we needed an integration of 70 minutes for a signal to noise ratio of 34 at 8,000 angstrom. And the magnitude of our object was around 19.8 magnitudes. In the I band, that's around 22, so a very faint object. So the physical parameter we have obtained for our object, so we have derived a spectral type of 0.3 with an error of 0.4. This was obtained by first optical visualization with other field object observed with the same instrument, L2 dwarf, L0 dwarf, and an M9, and we found that we had a better agreement with the L0. We also took some field object, what the spectra was taken in the literature, and we also did a visual inspection, and the best agreement was with L0. We used spectral indices. We also obtained the RMS by different normalization point. This gave us different values of spectral type, and this is where we got our L0.3. This was the average, and the standard deviation was 0.4. The effective temperature was obtained using spectral type and effective temperature relations. We had 3 of them. We took the average and added the error in quadrature. This gave us 2,300 Kelvin with an error of 370. Using the BT settle model from France Allard, a very recent model, this gives us a mass of 71 Jupiter mass. It's very close to the hydrogen burning limit. However, considering the error bar, we cannot say if it's above or below the hydrogen burning limit. Now, the L dwarf candidate, how could we assess the membership? Well, of course, it was selected by astrometry and photometry. So based on astrometry and photometry, it is a member of the cluster. It is within 3 sigma of the selection by astrometry, but also it is within 1.5 to be more precise, and also the photometry of this object makes it being located at the position of the sequence. It even is located at what we could say the binary sequence, but I will come back to this later. We, of course, cannot observe H alpha and the lithium because we don't have the resolution, but also because the signal is too bad at these wavelengths. However, we can make measurement of the unresolved sodium duplet. And these are the values. As you can see, for our target, the values of the equivalent with it of the sodium is lower than those of the field, which would expect if it's a younger object. And also we estimate a probability membership for our object. So basically what we did, we used the density of L0 dwarf from Caballero in the field. Then we defined the volume of our survey, and then from this we were able to estimate that there would be 16 L0 dwarf at the location of Praesepe that would have been selected by photometry. And then with proper motion, well, we know that it could be L dwarf with proper motion as high as 67 millarc second. This was obtained considering that you have in this work some L dwarf with tangential velocity that would be as high as 100 kilometers per second for L dwarf, put it at the location of Praesepe that would correspond to this proper motion. So in the vector point diagram, you have members that would cover an area of 14,000 millarc second square. Since our target is within 1.5 sigma of the cluster, this gives an area of 175 millarc second per square. The ratio of this is about 2.5% times 16. This is roughly 0.205 field L dwarf that could have been selected by photometry and astrometry and would be consistent with Praesepe, from which we get the membership probability of 79.5%. And also we went a step further to check if it was a member of the cluster. We used spectral type versus absolute K magnitude relation to check if it was having a magnitude consistent to what we would expect if it would be at the distance of Praesepe. It does, but it is in both cases 0.75 magnitude brighter, which would suggest that it's a binary. And indeed, as I've mentioned previously, by looking at the location of the L dwarf candidate, it may suggest that it's actually at the location of where we have the binary sequence. So future work, well, I had discussion with Nicola, and I've heard that it could be interesting and possible to try to observe the lithium at this wavelength, but apparently this would need 6 hours of OSIRIS GTC time. And then, well, in the same project, we also have several spectroscopic follow-up in undercluster. This I've mentioned. We also have other L dwarfs in the Pleiades. And then this is an example of how observation of L dwarf in other cluster would be important. In our previous work on Praesepe, the publication we had last year, we have noticed that the mass function of Praesepe is more similar to the one of the Alpha pair and Pleiades, although these are very young cluster compared to Praesepe. We would have expected it to be more similar to the Hyades. Well, one of the explanations could be that actually the mass function presented by Jérôme Dubouvier of the Hyades is incomplete. If we had in the last bin 12 L dwarf candidates from Hogan et al. 2008, then we would have a better consistency between the mass function of Praesepe and the Hyades. So just to sum up, I present you a L dwarf that was in a cluster candidate list of an astrometric and photometric astrometric survey in the Praesepe. We had a campaign of doing a spectroscopic follow-up of object with a mass lower than 0.1 solar mass in Praesepe Pleiades alpha pair. Our L dwarf candidate has the following physical properties. It's a L dwarf of type L0.3, an effective temperature close to 2,300, and a mass that puts it very close to the hydrogen burning limit at 71 Jupiter mass. We assess its membership based on photometry, astrometry, and of course the measurement of the unresolved pseudo doublet. We estimate a probability of membership of around 80%. Spectral type versus absolute K-band magnitude relation suggests that it's a binary, but also based on the location of this object and the color magnitude diagram. And all the detail of this work is presented in a publication in monthly notices that was accepted by the referee. The referee told us. But then we just wait the editor to click on the button accepted, and then it will be on AstroPH. So that's it. Thank you very much.
Okay, thank you very much, Steve. So now there is some time for questions. So, Jackie?
Steve, have you looked for astrometrical, I mean proper motions?
So yeah.
Proper motions.
Yes.
Have you looked
I'm sorry, I don't. What's your question?
proper motions?
Yes.
How say are coincident with known values of Praesepe?
Your question is actually how confident we are with that it's in the location of Praesepe in the vector point diagram. So that's the location actually of our target with the error bars. The blob here is the location of Praesepe in the vector point diagram.
Okay, and you showed us wavelengths of lithium line. It's very interesting wavelengths. Maybe it is wrong. Look, next one. Lithium line.
Yeah.
Wavelengths. The next slide, please. Next slide, please.
Next one. This one.
Next one. Next.
Next.
Next one.
I think. Yeah.
It is not lithium. It is H alpha.
Okay. Yeah, I mixed up. The thing is, yeah. We want to measure the lithium. It's not. It's the wavelength is wrong, but it's the lithium that.
It is another wavelength, yeah? Because. Yeah, sure.
Yeah.
Okay, so do you have any additional questions?
On the very last slide where you saw the IMFs and you say that they are different, I think this. Do you have an estimate of error bars there? Because I guess this is very small.
The error bars that we would have at that point are basically Poisson. The difference is between the IEDs and Praesepe in these last bin is up to 1 dex. Last year, when we were working on the proposal for the spectroscopic form, we were discussing with one of the theoreticians, Carsten Weitman, and to have such a discrepancy, it is, if I remember correctly, when you said that it was up to 1 dex, it's significant. As for the error bars, they are Poissonian. I would say it's probably in the scale of 1 or 2 sigma, but I would have to look at the numbers. But the point here is basically that this mass function of the IEDs would be incomplete because it does miss the L dwarf that are in the IEDs. It's a mass function of Jérôme Bouvier. And beside the 2 T dwarfs in their work and an object that is close to 0.1 solar mass, it doesn't include the L dwarf from Hogan et al. 2008.
More questions? Well, if not, I would like to make a comment. It's about the sodium line of this object. In Farah, if the age of Praesepe is real 600 million years, I didn't expect a very strong difference between field dwarfs and L dwarfs in Praesepe. But this difference is real. Maybe it could indicate that the age of Praesepe could be slightly lower, let's say 300 million years or something like that. So more close to the Pleiades than to the field.
I've looked at the model, the BT shuttle model from France Allard, and for that mass, the difference in log G between 600 million years and 1 gigayear would be 0.5 dex. And if you compare between 600 million years and 5 gigayears, it goes up to 0.1 dex. But how this reflect in equivalent width of unresolved sodium line, then this I don't know.
Yeah, well, the other question is, of course, that maybe you need to compare also with field dwarfs obtained with the same resolution, because sometimes now
these ones
you mentioned,
it was done. It's
with the same
with the same instrumental setup. Yeah.
That's right. So, any additional comments or questions? So, let's thank again Steve for